Neutron stars are the strangest objects in the universe, born from explosions crushed into city-sized cores, yet heavier than our Sun. Some collide, some become magnetars, and others spin as cosmic clocks we call pulsars. In this video we'll explore their incredible science. If you enjoy it, please like, subscribe, share, and tell us in the comments which type of neutron star fascinates you most. Thank you for watching. Now let's begin. A massive star spends millions of years steadily fusing lighter elements into heavier ones within its core. First hydrogen fuses into helium, then helium into carbon and oxygen, and later into heavier nuclei like neon silicon and finally iron. At each stage, the reactions release energy that balances gravity, keeping the star stable. But when iron accumulates, fusion can no longer yield net energy. The core becomes increasingly dense, reaching conditions where electrons are forced into protons to form neutrons, releasing neutrinos in the process. This sudden loss of electron pressure triggers collapse. The inner core contracts to nuclear densities in less than a second, forming a proto-neutron star. In that moment, the core reaches densities of several times the density of an atomic nucleus, packing a mass greater than the Sun's into a sphere about 20 kilometers across. The collapse halts abruptly due to the repulsive components of the strong nuclear force, producing a stiff rebound. A shock wave forms at the boundary between the inner and outer core. This shock attempts to move outward, but initially stalls as it loses energy, while dissociating heavy nuclei and radiating neutrinos. Without revival, the star would fail to explode and matter would simply fall back. What rescues the explosion is the outward streaming of neutrinos. The newly formed proto-neutron star emits an enormous flux of neutrinos of all flavors. Over the first seconds, nearly all of the gravitational binding energy of the star, about 10% of its mass energy, escapes in neutrinos. Some of these interact with matter just behind the stalled shock depositing energy. This reheating revives the shock, allowing it to accelerate outward again. The revived shock pushes through the outer layers of the star, disrupting it, in what observers see as a core collapse supernova. The expelled material includes oxygen, silicon, and iron, enriching the interstellar medium with the raw ingredients for new stars and planets. The remnant that stays behind is the proto-neutron star. During the first seconds after birth, this compact object cools rapidly by radiating neutrinos. The temperature in the core may exceed tens of billions of degrees at the moment of formation. As neutrinos carry energy away, the star contracts slightly and becomes stable. Within about a minute, the neutrino emission subsides, and the proto-neutron star transitions into a neutron star proper. Its crust solidifies, magnetic fields freeze into place, and rotation settles into a steady pace. The mass of the newborn neutron star depends on how much of the surrounding material falls back after the explosion. If the remnant is below about 2.5 times the mass of the Sun, it remains a neutron star. If it is heavier, gravity overwhelms even nuclear forces, and a black hole forms instead. Observations confirm neutron stars with masses close to 2 solar masses, showing that they can withstand enormous pressures before collapsing further. From a distance, a newborn neutron star may be detected as a bright X-ray source if its surface remains hot or if it interacts with surrounding material. Over time, however, the surface cools and it shines mainly in soft X-rays or faint visible light. The true signature often comes later when its magnetic field and rotation combine to power radio pulses or high-energy emissions. These phenomena reveal the extreme compactness of the object, but the formation itself is hidden deep inside the supernova's blast. Supernova remnants such as the Crab Nebula preserve records of these explosive events. At their centers, astronomers sometimes find pulsars confirming the link between core collapse explosions and neutron starbirth. The timing of the pulses shows the object's rapid spin, a result of angular momentum conservation. Just as a spinning skater turns faster when pulling in their arms, the collapsing star spins up dramatically as its core contracts from thousands of kilometers across to only a few tens. Spin periods of newborn neutron stars can be as short as a few milliseconds. The strength of the magnetic field also traces back to the progenitor star. During collapse, magnetic flux is conserved and field lines are compressed. What began as a modest stellar magnetic field can intensify to trillions of Gauss in the compact remnant. In some cases, turbulence and dynamo processes amplify the field even more, producing magnetars with fields thousands of times stronger. The field influences how the neutron star radiates and how it interacts with its surroundings from the moment of birth onward. Another key process in these first moments is fallback accretion. Not all of the outer layers necessarily escape the explosion. Some matter can reverse course pulled back by gravity onto the compact object. This can increase the neutron star's mass spin it further, and in extreme cases push it past the threshold for black hole formation. Whether a neutron star survives depends delicately on the balance between explosion energy and fallback mass. This explains why some massive stars leave black holes, while others leave neutron stars even with similar initial conditions. The formation of a neutron star is thus a balance of collapse-rebound neutrino physics and subsequent cooling. Each step is grounded in well-tested physics, but observed indirectly. Neutrino burst from supernova 1987A provided a brief glimpse of the core collapse process, confirming theoretical expectations. Future neutrino observatories aim to capture many more events, allowing detailed study of the cooling and birth sequence. Meanwhile, gravitational wave detectors hold promise to record the collapse dynamics themselves, offering another window into the dense core. In this way, the path from a massive star to a neutron star is one of the most dramatic but also most fundamental processes in stellar evolution. The death of the star provides the conditions for the creation of one of the most compact and exotic states of matter known. The newborn neutron star carries forward the angular momentum magnetic flux and dense matter physics set in motion during those final seconds. From here, it will cool spin and evolve into the varied population of neutron stars that astronomers observe across the galaxy. Inside a neutron star, the defining property is the balance between pressure and density, a relationship called the equation of state. It describes how a matter resists compression under conditions far beyond those achievable in laboratories on Earth. In normal stars, pressure comes from heat and radiation. In white dwarfs, it comes from electrons pressed into a degenerate state. In neutron stars, the pressure arises from neutrons packed together at densities several times greater than those in atomic nuclei combined with the effects of nuclear forces that operate at the smallest scales. The precise relation between pressure and density is unknown, yet it governs the star's size, its maximum mass, and how it deforms under extreme conditions. Scientists begin with known nuclear physics. At densities similar to those in nuclei, interactions between nucleons are relatively well described by laboratory experiments and by quantum calculations. But as density rises to several times nuclear saturation, new uncertainties appear. The interactions may include not only simple two-body forces, but also three-body forces where three nucleons influence one another at once. The behavior of such forces is not fully mapped. Different theoretical approaches give different stiffness of the equation of state. A stiffer relation means higher pressure at a given density, leading to larger stars that can support more mass. A softer relation means lower pressure producing smaller stars and lowering the maximum stable mass. Astronomers gain constraints from observing neutron stars in binaries. When a neutron star orbits another star, careful tracking of orbital motion allows precise mass measurement. Several neutron stars have been weighed in this way and found to have masses close to 2 times that of the Sun. This fact alone rules out many soft equations of state, because such models would not allow a neutron star to reach that mass without collapsing into a black hole. The existence of 2 solar mass neutron stars demonstrates that pressure remains strong even at extreme density. Determining radii is more difficult. One method uses X-ray observations of hotspots on rotating neutron stars. As the star spins, hotspots sweep across the line of sight. Light bending by strong gravity alters the apparent pulse shapes. By modelling these shapes, scientists can estimate both mass and radius. Another method relies on thermonuclear bursts in accreting neutron stars, where material on the surface undergoes runaway fusion. The expansion and cooling of the surface layers imprint signatures in the light curve that depend on the star's size. Both methods suggest typical radii around 11 to 14 kilometers for neutron stars with masses near 1.5 times that of the Sun. Additional evidence comes from gravitational wave astronomy. When 2 neutron stars orbit each other closely, they exert tidal forces that distort their shapes. These distortions affect the orbital motion and leave an imprint on the gravitational waves emitted. The first observed neutron star merger in 2017 allowed direct measurement of this tidal deformability. The results favoured equations of state that are neither extremely stiff nor extremely soft, narrowing the allowed range. With more mergers recorded in the future, the constraints will become tighter, gradually revealing the pressure-density relation more clearly. Cooling also offers clues. A newborn neutron star shines by emitting neutrinos rather than photons. For the first 100,000 years, neutrino emission is the dominant cooling process. The rate of neutrino loss depends on the microscopic reactions allowed in the core. If only slower processes called modified Urca reactions are possible, cooling is gradual. If direct Urca reactions operate involving simple beta decay, and its inverse cooling accelerates. Whether direct Urca is allowed depends on the proton fraction set by the equation of state. Observations of young neutron stars therefore provide indirect hints. The object in Cassiopeia A, for instance, has been seen to cool more rapidly than expected, suggesting that direct Urca or related fast neutrino processes may indeed occur. Theoretical models extend even further, proposing that at the highest densities neutrons might dissolve into their constituent quarks. This would form a new state of matter sometimes called deconfined quark matter. Some versions predict a gradual crossover, others predict a sharp phase transition. If such a transition occurs, neutron stars of certain masses might contain quark cores, or even become hybrid stars with layers of different phases. Another possibility is the appearance of hyperons particles containing strange quarks. Their presence would soften the equation of state, making it difficult to support the heavy neutron stars already observed. Reconciling the existence of massive stars with the possibility of hyperons remains an active problem in dense matter physics. To compare models with data, scientists build families of possible equations of state. Each must be consistent with known nuclear physics at lower densities. Each must allow a maximum mass above 2 solar masses. Each must also fit the measured ranges of radii and tidal deformabilities. As observations accumulate, the range of acceptable models narrows. Those predicting too small or too large radii are excluded. Those unable to support the most massive known neutron stars are rejected. The surviving possibilities form a corridor of likely behavior, though not yet a single unique solution. This work highlights the role of neutron stars as natural laboratories. No terrestrial experiment can compress matter to such densities for long periods. Colliders can create dense states briefly, but neutron stars sustain them for millions of years. Every observation of their masses, radii, cooling and merger signatures provides data about the strong nuclear force under conditions impossible to replicate elsewhere. The study of the equation of state therefore links astrophysics with fundamental physics, bridging the behavior of stars and the structure of matter at its most basic level. Current evidence points to neutron stars having radii of about 12 kilometers and maximum masses just over 2 solar masses. The pressure inside must be strong enough to resist collapse, but the exact composition of the core is still uncertain. Whether it contains only neutrons and protons, or whether more exotic forms of matter emerge is not yet resolved. Each new observation, whether in X-rays, gravitational waves, or neutrinos, adds another constraint. Over time, these pieces combine into a more complete picture of how matter behaves at the highest densities found in the present universe. A neutron star is not uniform from surface to center. Its structure is layered, each region defined by distinct physics. At the outermost edge lies a thin atmosphere only a few centimeters deep. This atmosphere is composed of light elements, if the star has recently accreted material, or of heavier elements if it has not. Below the atmosphere lies the outer crust extending a kilometer deep. Here nuclei remain arranged in a lattice, but electrons are degenerate, moving freely through the structure. As depth increases, nuclei become progressively more neutron-rich. Eventually, neutrons begin to drip out of nuclei, creating a mixture of free neutrons and neutron-rich nuclei. This marks the transition to the inner crust. The inner crust extends several kilometers and contains matter unlike anything on Earth. Here, free neutrons coexist with a lattice of nuclei and a sea of electrons. At these densities, the free neutrons may become superfluid, flowing without viscosity. This region plays a key role in the dynamics of the star, especially in phenomena like pulsar glitches. The lattice of nuclei provides a rigid framework that anchors magnetic fields, while the superfluid neutrons carry angular momentum in quantized vortices. These features connect the microscopic physics of nuclei with macroscopic observations of rotation. Deeper still lies the outer core. In this region, matter consists mostly of neutrons with a small fraction of protons, electrons and muons. The density here is several times nuclear saturation density. Protons are believed to form a superconducting fluid, while neutrons remain superfluid. The presence of superconductivity means magnetic fields may be arranged in quantized flux tubes, while superfluidity means rotation is carried by quantized vortices. The interaction between vortices and flux tubes influences how angular momentum and magnetic energy evolve over time. At the very center lies the inner core. This region is the least certain, as no experiment can reach such densities. It may contain only nucleons, or it may host hyperons, Bose condensates of mesons or deconfined quark matter. The transition between outer core and inner core is not directly observable, but it affects the star's mass-radius relation and its maximum stable mass. If quark matter forms smoothly, the star may have a continuous structure. If a sharp transition occurs, the star could have a distinct core of exotic matter. These possibilities remain open questions in dense matter physics. The crust is particularly important for observable phenomena. Its lattice provides rigidity that allows the star to support mountains no taller than a few centimeters. These tiny deformations combined with rapid rotation may produce continuous gravitational waves. So far, no detection has been made, but future observatories may be sensitive enough to find them. The crust also controls thermal conductivity, regulating how heat moves from the core to the surface. During accretion, material builds up on the crust, compressing deeper layers and triggering nuclear reactions. These reactions heat the star from within, and when accretion halts, the crust cools in a predictable way. Observations of such cooling provide information about conductivity and specific heat. The transition between crust and core is also of interest. As density rises, nuclei become extremely neutron-rich and large. Eventually, they may form exotic shapes collectively called nuclear pasta. Sheets, rods, and bubbles of nucleons may appear resembling structures seen in soft condensed matter, but governed here by nuclear forces. These shapes minimize energy under competing conditions of nuclear attraction and Coulomb repulsion. Their presence alters thermal and electrical conductivities, influencing how the star evolves over long timescales. Superfluid neutrons in the inner crust influence rotational behavior. They store angular momentum in vortices that can become pinned to the crustal lattice. When they suddenly unpin, angular momentum transfers to the crust, causing the star to spin slightly faster in an event called a glitch. Observations of glitches in pulsars reveal abrupt increases in rotation rate, followed by slow relaxation. These events demonstrate that superfluidity exists inside the star, connecting theory with observation. The layering also influences magnetic field evolution. Fields anchored in the crust can decay over hundreds of thousands of years, while fields coupled to the superconducting core may evolve differently. This interaction explains why some neutron stars retain strong fields for millions of years, while others decay more rapidly. The layered interior therefore determines not only structure, but also the observable life of the star. Models of neutron star interiors must satisfy all observed constraints: maximum mass radii, cooling behavior, glitch dynamics, and field evolution. Different assumptions about the composition of the core or the properties of superfluids lead to different predictions. Step-by-step observations narrow these assumptions. For example, the rapid cooling observed in the neutron star in Cassiopeia. A may indicate the onset of neutron superfluidity in the core. Glitches observed in the Vela pulsar indicate strong coupling between crust and interior. These pieces of evidence guide refinements of interior models. Although the deepest core remains uncertain, the overall picture is consistent. A neutron star is composed of an outer atmosphere, a solid crust with neutron-rich nuclei, a region of free neutrons forming a superfluid, and a core dominated by neutrons with smaller fractions of other particles. The balance of pressure and gravity compresses matter into forms never produced elsewhere, yet still obeying the same fundamental interactions. This layered structure explains why neutron stars are stable for millions of years, why they radiate in diverse ways, and why they occasionally reveal sudden changes in spin or emission. From surface to center, the star thus transitions from familiar atomic matter to increasingly exotic forms. Each layer is inferred from nuclear physics, theoretical models, and astrophysical observations. None of these layers can be seen directly, but together they form a coherent understanding of how matter organizes itself under extreme compression. The study of these layers is ongoing, with each new observation of thermal emission, pulsar timing, or gravitational wave signal adding to the picture. Neutron stars therefore remain both extraordinary objects in space and unique probes of physics at densities otherwise unreachable. At the boundary between the inner crust and the outer core, matter organizes itself in unusual and complex ways. When nuclei become extremely neutron-rich and crowd together under immense pressure, They no longer remain as neat spheres in a lattice. Instead, they form extended structures, sometimes described as resembling shapes of pasta. Long rods of nucleons resemble spaghetti, flat sheets resemble lasagna, and bubble-like voids resemble Swiss cheese. These structures arise because of the competition between the strong nuclear force which holds nucleons together and the Coulomb force which repels protons from each other. At these densities, neither force dominates, and the lowest energy arrangement involves these intermediate, partially ordered shapes. The nuclear pasta region is thought to extend for hundreds of meters inside the star. Though small in size compared to the whole star, it has an outsized effect on observable properties. The geometry of these structures influences how electrons scatter, which in turn controls electrical and thermal conductivities. Conductivity governs how quickly the magnetic field evolves and how efficiently heat flows from the core to the surface. In this way, the existence of nuclear pasta may affect how bright a neutron star appears in X-rays long after its birth. Another key influence of pasta structures is on neutrino transport. Neutrinos carry energy out of the star, especially during the early cooling phase. Their scattering probability depends on the arrangement of nucleons. Extended shapes like rods and sheets scatter neutrinos differently than spherical nuclei. This alters the rate of energy loss. Cooling curves derived from observations of young neutron stars can therefore provide indirect evidence for the presence of pasta phases. While no direct detection is possible, consistency between theoretical predictions and observed cooling supports the idea that nuclear pasta is real. Simulations of nuclear pasta rely on advanced computational methods. Quantum molecular dynamics codes track millions of nucleons under realistic forces. These simulations show spontaneous formation of rod-like and sheet-like arrangements as density increases. They reveal that defects and disordered regions also appear much like imperfections in terrestrial crystals. Such imperfections can pin superfluid vortices, providing additional connections to observable glitch phenomena. The picture that emerges is not one of perfect order, but of a dynamic semi-ordered layer that shapes the behavior of the entire star. The presence of nuclear pasta may also influence magnetic field decay. If the crust is more resistive due to pasta structures, magnetic fields could decay on shorter timescales. This effect may help explain why some neutron stars retain strong fields for only a few 100,000 years, while others evolve more rapidly into objects with weak or undetectable fields. In particular, magnetars with extremely strong magnetic fields may owe part of their activity to interactions between their fields and the resistive pasta layer. As stresses build up, they may crack the crust or rearrange magnetic lines, triggering bursts of high-energy radiation. Thermal conductivity in the pasta region influences the temperature distribution on the surface. A crust with high conductivity transports heat evenly, leading to uniform emission. A crust with lower conductivity allows temperature variations to persist, producing hotspots that rotate into and out of view. Observations of pulsed X-ray emission from isolated neutron stars suggest that such temperature variations exist, pointing again to the influence of interior layers. Although the term pasta is descriptive, the structures are not visual features but inferred arrangements of matter at the femtometer scale. They illustrate how complex organization can arise from fundamental forces even under extreme compression. Their role is not decorative but functional, altering the macroscale properties of the star. In effect, the nuclear pasta layer acts as a mediator between the solid crust above and the fluid core below. It carries imprints of both regimes, and its properties shape how the star behaves over thousands to millions of years. Evidence for nuclear pasta is circumstantial but growing. Models of cooling that include it fit observed temperature evolution better than those without it. Calculations of crust-breaking strains suggest that pasta is stronger than steel by several orders of magnitude. This means the crust can support small deformations for long times, potentially emitting continuous gravitational waves as the star spins. Searches for such waves are ongoing with current gravitational wave observatories, though no detection has yet been made. Future instruments may reach the required sensitivity to confirm or rule out such signals. The pasta layer also matters for nuclear astrophysics more broadly. The arrangement of nucleons in sheets or rods changes how reactions occur under compression. In accreting systems where fresh matter builds up on the surface and compresses older layers, the nuclear reactions that release heat may be influenced by whether nuclei below are spherical or extended. This modifies the heating profile of the crust and alters the thermal evolution once accretion halts. Observations of accreting neutron stars cooling after long outbursts provide an indirect probe of these processes. Theoretical uncertainties remain. Different nuclear force models predict different thicknesses and properties of the pasta region. Some suggest that it extends over only a narrow density range, while others find that it occupies a substantial portion of the crust. The exact effect on conductivities and neutrino scattering also depends on whether the structures are regular or contain many defects. Observations alone cannot yet distinguish these details, but combining cooling data, glitch statistics, and magnetic field decay patterns may eventually provide stronger evidence. In summary of the descriptive picture, the nuclear pasta layer sits quietly between the rigid outer crust and the fluid outer core. It consists of organized nucleon structures that alter transport properties. It affects neutrino scattering, magnetic field, evolution, heat conduction, and superfluid vortex pinning. Though hidden deep inside, it leaves fingerprints on surface emission and timing behavior. The study of this layer demonstrates how microscopic organization of matter under extreme conditions can govern macroscopic phenomena visible across the galaxy. When a neutron star rotates, it carries within it layers of matter that behave in different ways. The crust is solid, the protons in the core may be superconducting, and the neutrons in both the crust and core are expected to be superfluid. Superfluidity means that neutrons pair together and move without viscosity, allowing them to flow freely across macroscopic distances. Rotation in a superfluid is not continuous, but is carried by quantized vortices, each one a tiny tube where circulation is concentrated. The distribution and motion of these vortices control how the superfluid maintains angular momentum. This property becomes crucial in explaining sudden changes in neutron star spin known as glitches. In a rotating neutron star, the crust and the superfluid interior are not always locked together perfectly. The solid crust spins as a rigid body, gradually slowing due to electromagnetic radiation and winds emitted from the magnetosphere. The superfluid, however, can maintain its rotation more steadily. Its vortices may become pinned to the lattice of nuclei in the crust. When pinned, the vortices prevent the superfluid from slowing down, creating a growing lag between the interior and the crust. As this lag increases, stress builds at the pinning sites. Eventually, the vortices unpin in an avalanche, moving outward suddenly. Angular momentum is transferred to the crust, spinning it up slightly. To an observer, this appears as a glitch, an abrupt increase in the rotation rate of the pulsar. Glitches are observed in many pulsars, most notably in the Vela pulsar, which shows large glitches every few years. Each glitch is followed by a relaxation phase, where the rotation rate drifts slowly back toward the expected trend. This recovery reflects the gradual recoupling of the crust and superfluid, The timescale of recovery ranging from days to months provides direct information about how the interior fluids interact with the lattice and with each other. Thus, glitches are not just irregularities but probes of the microscopic physics inside neutron stars. The size of glitches varies widely. Some are tiny, barely measurable, while others are large enough to alter the pulse arrival times by milliseconds. This distribution suggests that vortices unpin both individually and in collective avalanches. The process resembles critical phenomena in other physical systems, though here it occurs in an environment of extreme density and magnetic fields. Models that treat vortices as interacting with pinning sites reproduce the observed statistics fairly well. Such models show that even slight changes in pinning strength or crust structure can shift glitch behavior dramatically. The interaction between vortices and magnetic flux tubes in the superconducting core may also contribute. Protons in the core are thought to form a Type II superconductor, where magnetic fields penetrate in quantized flux tubes. These flux tubes may become entangled with neutron vortices. Movement of vortices then requires dragging flux tubes, which resists motion and strengthens pinning. When vortices finally break free, they can move collectively, transferring a larger amount of angular momentum at once. This coupling may explain the largest observed glitches, which seem too strong to result only from crustal pinning. Timing observations reveal that glitches are not random. In some pulsars, they occur at semi-regular intervals, hinting at an underlying cycle of stress, build-up and release. In others, they are more irregular, suggesting that stochastic processes dominate. In either case, glitches show that neutron stars are dynamic, with their interiors continually adjusting to the loss of angular momentum through radiation. The rate at which they spin down sets the pace for vortex unpinning, and thus the frequency of glitches. Beyond glitches, timing irregularities include what is called timing noise, a more gradual wandering of the rotation period. The origin of timing noise is less well understood. It may involve slow changes in magnetospheric currents, or interactions between crust and core that do not produce sharp events. Glitches and timing noise together demonstrate that neutron star rotation, while often remarkably stable, is not perfectly so. The deviations provide windows into processes hidden beneath the surface. Superfluidity itself is a remarkable state. On Earth, superfluids such as liquid helium can flow endlessly through narrow channels without resistance. In neutron stars, the scale is vastly larger, yet the principle is similar. Pairs of neutrons move coherently unaffected by ordinary viscosity. Quantized vortices carry the rotation, ensuring that the angular momentum is preserved. The density and pressure of the environment are so extreme that the coherence length of these pairs is very small, yet the effect on global behavior is profound. The study of glitches has practical consequences. Pulsars are used as precise cosmic clocks, their pulses arriving with remarkable regularity. A glitch alters the timing, which must be accounted for in applications such as pulsar navigation, or searches for gravitational waves using pulsar timing arrays. By modeling the glitch behavior, astronomers can correct the pulse records and continue to use them as stable references. Thus, understanding the superfluid interior is not only of theoretical interest, but also of practical importance for astrophysical measurements. The connection between microphysics and observation is striking. At the scale of femtometers, neutrons pair and vortices pin to nuclei. At the scale of kilometers, angular momentum shifts between layers. At the scale of astronomical observations, pulses from thousands of light-years away arrive earlier than expected, revealing the change. Glitches therefore link quantum behavior with galactic-scale signals. Continued monitoring of pulsars will expand the sample of glitches. Each event refines the models of pinning strength vortex dynamics and coupling between crust and core. The diversity of observed behavior suggests that different stars may have different interior conditions, perhaps reflecting variations in crust thickness, temperature, or magnetic field structure. In this way, pulsar timing builds a comparative science of neutron star interiors, one glitch at a time. Magnetic fields are among the most striking features of neutron stars. When the core of a massive star collapses, the magnetic flux is conserved. Field lines that once stretched across the radius of a giant star are compressed into a sphere only a few tens of kilometers wide. This compression alone can raise magnetic strengths to trillions of Gauss. In some neutron stars, additional amplification mechanisms may operate, such as turbulent dynamos, during the first seconds of life-raising fields even further to values exceeding 100 trillion Gauss. Such extreme fields are difficult to imagine, but play a central role in shaping the behavior of these compact stars. Around the neutron star, the magnetic field extends outward into space, creating a region called the magnetosphere. This region is filled with charged particles drawn from the surface and accelerated along magnetic lines. The structure of the magnetosphere depends on the rotation of the star. Close to the surface, field lines are anchored and may form closed loops. Beyond a certain distance, called the light cylinder, the speed required for co-rotation equals the speed of light, and field lines must open. This division between closed and open field regions determines how plasma flows and where radiation is produced. The magnetosphere acts as a machine that converts rotational energy into electromagnetic emission. As the neutron star rotates its strong field, induces electric fields that accelerate particles to relativistic speeds. These particles produce radio waves, X-rays and gamma rays through processes such as curvature radiation and synchrotron radiation. The outgoing particle winds also carry away angular momentum, gradually slowing the star. The breaking rate depends on the strength of the field and the spin period. Young pulsars with strong fields slow rapidly, while millisecond pulsars with weaker fields spin for billions of years. Observations across the electromagnetic spectrum reveal the structure of magnetospheres. In radio wavelengths, beams of coherent emission sweep across Earth as pulses. In X-rays and gamma rays, broader emission patterns show where energetic particles collide with the surface or interact in the outer magnetosphere. The Crab pulsar, for example, shines in radio-optical X-ray and gamma-ray bands, each revealing different aspects of its field and plasma environment. This multi-wavelength view confirms that the magnetosphere is a dynamic region where fields and particles interact continuously. The magnetic field also affects the star's surface. Charged particles accelerated in the magnetosphere can strike localized regions, heating them into hotspots that glow in X-rays. The locations of these spots trace the geometry of the field, which may not be a perfect dipole but can include higher-order multipoles. In some cases, the surface field may be much stronger in local patches than in the global average. These irregularities influence emission patterns and complicate attempts to infer the field from timing measurements alone. Over long timescales, magnetic fields evolve. Currents flowing in the crust and core gradually dissipate energy. If the core contains superconducting protons, the magnetic field is confined to quantized flux tubes. Movement of these tubes and their interaction with superfluid vortices determines how the field changes over millions of years. Some neutron stars show evidence of rapid decay, their fields weakening by orders of magnitude within 1 million years. Others maintain strong fields far longer. These differences suggest that interior conditions such as temperature composition and superfluidity play critical roles in field evolution. Magnetars represent the extreme case. Their fields exceed 100 trillion Gauss, strong enough to stress the crust to breaking. When the crust yields, magnetic energy is released suddenly. This produces short bursts of X-rays or gamma rays, sometimes lasting less than a second, but radiating more energy than the sun emits in years. On rare occasions, giant flares occur, releasing even greater energy. These events demonstrate that magnetic fields are reservoirs of immense power. They also confirm that the crust and magnetosphere are coupled through stresses and reconnections. Theoretical models of magnetospheres seek to capture these interactions. Force-free simulations where fields dominate plasma motion show how rotation twists field lines and launches winds. More detailed magnetohydrodynamic models include plasma inertia and resistivity, capturing reconnection events and current sheets. These models reproduce observed pulse profiles and spectra linking field geometry to emission, yet uncertainties remain, especially in how coherent radio emission is generated. Despite decades of study, the precise mechanism behind pulsar radio pulses is not fully understood. Measurements of breaking indices provide additional information. The rate at which spin slows is expected to follow a simple power law if only dipole radiation operates. Observed indices often differ, indicating that other processes contribute, such as changes in field strength, alignment of magnetic and spin axes, or contributions from winds. These deviations show that the magnetosphere is not static but evolves as the star ages. Young pulsars often have complex environments with strong winds and nebulae, while older pulsars show quieter magnetospheres. The magnetosphere also interacts with surrounding space. Pulsar winds inflate nebulae visible in X-rays and radio as glowing bubbles of shocked plasma. These pulsar wind nebulae show wisps, jets, and toroidal structures shaped by the magnetic field. The Crab Nebula is the best-known example where the central pulsar powers a bright and dynamic nebula. Observations of these structures provide further tests of magnetospheric models, since the outflows carry signatures of field strength and particle acceleration. Magnetic fields are thus central to every observable property of neutron stars. They channel particles, regulate emission, power pulsar winds, and sometimes unleash violent flares. Their strength ranges from billions to hundreds of trillions of Gauss, far beyond laboratory values. Their evolution connects microphysical processes inside the star to large-scale astrophysical phenomena. In studying neutron star magnetospheres, astronomers explore not only exotic stellar remnants, but also the limits of magnetic phenomena in the universe. Radio pulsars are the most iconic representatives of neutron stars. They appear as steady beacons in the sky, sending pulses of radio waves with remarkable regularity. The mechanism behind these pulses begins with the rotation of the neutron star and the orientation of its magnetic axis. The magnetic poles are usually misaligned with the spin axis. Radiation generated near the poles escapes in narrow beams that sweep across space as the star rotates. When one of these beams intersects Earth, astronomers detect a pulse. This lighthouse effect is not a visual light flash, but a sequence of radio emissions tied precisely to the star's spin. Pulsars were first discovered in 1967 through regular bursts of radio signals that repeated every second or so. At first, the precision of the pulses seemed so unlikely that some considered extraterrestrial origins. But soon many more were found, showing that they are natural phenomena linked to collapsed stars. Today, thousands of pulsars are known, each with a characteristic spin period and slowdown rate. These properties are measured by recording the arrival times of pulses with high precision. The rotation periods of pulsars span a wide range. Some rotate once every few seconds, while the fastest known rotate more than 700 times per second. Young pulsars usually spin faster, and slow down steadily as they radiate energy. Old pulsars found in binary systems can be spun up again by accreting matter from a companion. These are called millisecond pulsars. Their extremely fast rotation and stability make them cosmic clocks of extraordinary precision. The regularity of pulsar timing has practical uses. Arrays of millisecond pulsars are monitored to detect gravitational waves passing through the galaxy. As a wave stretches and compresses space, the arrival times of pulses shift slightly. By comparing many pulsars across the sky, astronomers can search for correlated timing variations that reveal the presence of waves from merging supermassive black holes. Pulsars thus extend gravitational wave astronomy to much lower frequencies than ground-based detectors can reach. The emission mechanism of radio pulsars involves the acceleration of particles in the magnetosphere. Electric fields induced by the rotating magnetic field pull electrons and positrons from the surface. These particles are accelerated along magnetic field lines and emit radiation as they curve. The process may also trigger cascades of pair production, filling the magnetosphere with plasma. Exactly how coherent radio emission arises from these particles remains uncertain. Various models propose that bunches of charges radiate in unison, or that plasma instabilities amplify the emission. What is clear is that the emission is tied to the rotation and magnetic geometry of the star. Pulsar beams are not uniform. Some have narrow cores, others show wide cones or multiple components. The shape depends on where in the magnetosphere the emission arises. By studying pulse profiles at different frequencies, astronomers map the emission regions. Higher frequency radiation often comes from closer to the star, while lower frequency emission originates further out. Polarization measurements provide further clues, showing how magnetic fields twist the direction of the waves. These detailed observations allow reconstruction of the geometry of individual pulsars. Timing stability is one of the defining features of pulsars. For many, the rotation can be predicted with extraordinary accuracy over years. The most stable rivals atomic clocks in precision. This makes them useful for testing fundamental physics. Pulsar timing has confirmed the existence of gravitational waves indirectly through orbital decay in binary systems. It has placed tight limits on the variability of fundamental constants. It has even been proposed as a method for spacecraft navigation using pulsars as natural beacons across the solar system. Not all pulsars are equally stable. Some show timing noise, slow, irregular drifts in their rotation. Others exhibit glitches as described earlier with sudden changes in spin. These deviations must be accounted for when using pulsars as precise clocks. Still, the overall stability of many pulsars remains extraordinary, especially among millisecond pulsars. The combination of rapid spin and weak magnetic fields in these stars appears to minimize irregularities, producing long-term regularity. Pulsars emit not only radio waves. Some shine in optical X-ray or gamma-ray bands as well. These emissions arise from energetic particles in the outer magnetosphere, or from hotspots where particles strike the surface. Observations across multiple wavelengths give a fuller picture of how pulsars operate. For example, the Crab pulsar produces sharp pulses in both optical and gamma rays, aligned with its radio pulses, showing that emission occurs at several altitudes simultaneously. The discovery of pulsars revolutionized astrophysics by providing a new tool for studying compact objects. They revealed that neutron stars exist, confirmed theoretical predictions about stellar collapse, and opened new fields of research. Each pulsar carries information about the density, magnetism, and rotation of its interior, conveyed through the rhythm of its pulses. By collecting and comparing thousands of such signals, astronomers build a statistical view of neutron star populations across the galaxy. Pulsars also interact with their surroundings. Their winds inflate nebulae, creating glowing bubbles of relativistic plasma. Their motion through space can generate bow shocks in the interstellar medium. These interactions produce additional emissions visible in X-ray and radio. By studying pulsar wind nebulae and bow shocks, astronomers can learn about the energy output and velocity of the star. Thus, pulsars not only act as clocks, but also as engines powering larger structures. The enduring mystery of pulsars lies in their emission mechanism. Despite decades of study, the precise details of how coherent radio pulses arise remain unsettled. Yet this uncertainty does not hinder their usefulness. Astronomers exploit their stability for tests of gravity, for detection of gravitational waves, and for exploration of the interstellar medium. Each pulse travels through interstellar plasma where it is dispersed and scattered. By measuring these effects, scientists map the distribution of electrons along the line of sight. In this way, pulsars become probes of both fundamental physics and galactic structure. The population of pulsars continues to grow as new surveys search deeper into the sky. Sensitive radio telescopes like FAST in China and the Square Kilometre Array under construction will uncover many more. Each new detection expands the catalogue and provides more precise clocks for timing arrays. As the sample grows, patterns in their distribution ages and properties will refine our understanding of neutron star evolution. Radio pulsars therefore stand at the intersection of astrophysics and fundamental physics. They are compact remnants of stellar death, yet they provide tools to test theories of gravity, matter, and space-time. Their beams sweep across Earth with clock-like precision, carrying with them information from deep inside one of the most extreme states of matter in the universe. While many pulsars emit with clock-like steadiness, their signals are not always perfectly regular. Subtle deviations reveal ongoing processes inside and around the star. Among the most striking are glitches, sudden increases in rotation frequency, which connect to the behavior of superfluid vortices as described earlier. But between these large events lie smaller irregularities collectively known as timing noise. Timing noise appears as slow wanderings in the measured arrival times of pulses. It is not caused by observational error but reflects real changes in the star's rotation or emission. These irregularities highlight the dynamic nature of neutron stars, showing that even their apparent stability masks constant internal and external adjustments. Glitches themselves display a wide spectrum of sizes and recovery behaviors. After a glitch, the rotation frequency may relax toward the pre-glitch trend on timescales, ranging from days to years. This relaxation indicates that different regions of the star couple to the crust with varying strengths. Some layers recouple quickly, others more slowly. By analyzing the recovery, scientists infer the viscosity and mobility of superfluid components. This information cannot be obtained in laboratories, making pulsar glitches unique probes of dense matter hydrodynamics. The distribution of glitch sizes provides further insights. In some pulsars, many small glitches occur, frequently suggesting local unpinning of individual vortices. In others, rare but large glitches dominate, pointing to collective unpinning events, involving vast numbers of vortices. This pattern resembles avalanche dynamics in other systems such as earthquakes or avalanches of sand, though the physical setting here is nuclear matter deep inside a star. The similarity across scales underscores the universality of critical phenomena in nature. Timing noise distinct from glitches may arise from processes in the magnetosphere. Variations in particle currents can alter the torque applied to the star, producing slow drifts in rotation. Alternatively, differential rotation between the crust and the core may generate irregular coupling leading to noisy timing. Observations show that timing noise is more pronounced in young pulsars, which often have complex magnetospheres and higher internal temperatures. Older millisecond pulsars, in contrast, exhibit much lower levels of timing noise, reinforcing their role as precise clocks. One famous case is the Crab pulsar, which exhibits both frequent glitches and significant timing noise. Detailed monitoring over decades has shown a mixture of sudden spin-ups, slow drifts, and irregular relaxations. The complexity of its behavior reflects the combination of a strong magnetic field, active magnetosphere, and dynamic interior. The Vela pulsar, on the other hand, produces large glitches at relatively regular intervals with more predictable recovery. Comparing these two stars illustrates the diversity of neutron star behavior, even among well-studied objects. Glitches also affect emission properties. In some cases, the pulse profile or radio brightness changes immediately after a glitch, suggesting that the interior event couples to the magnetosphere. This connection implies that angular momentum transfer and magnetic field geometry are linked. By monitoring emission before and after glitches, astronomers probe how deep interior dynamics influence the outer plasma environment. Such links demonstrate that neutron stars cannot be understood as isolated layers, but must be studied as coupled systems. Theoretical models of glitches involve pinning and unpinning of vortices in the superfluid. Vortices pinned to the crustal lattice build tension as the crust slows down. Once the lag reaches a threshold, vortices move outward suddenly. The angular momentum they carry transfers to the crust, spinning it up. Simulations of vortex dynamics show that large-scale avalanches can emerge from local interactions. These models reproduce many features of observed glitch statistics. Still open questions remain, such as the precise pinning strength of vortices and the role of interactions with magnetic flux tubes in the core. Another observable link to timing irregularities is breaking index. In the simplest model of magnetic dipole radiation, the spin-down rate follows a predictable relation. Measured breaking indices often deviate from this value, sometimes significantly. These deviations may reflect evolving magnetic field strengths, alignment changes between magnetic and spin axes, or additional torques from particle winds. Thus, breaking index measurements provide further evidence that neutron star rotation is influenced by multiple evolving factors. The study of glitches and timing noise is not only important for understanding neutron star interiors, but also for applications of pulsar timing. Pulsar timing arrays require extremely stable signals to detect gravitational waves from distant sources. When a pulsar glitches, its data must be carefully corrected or excluded. By modeling the physics of glitches and noise, astronomers can compensate for these irregularities and maintain the sensitivity of timing arrays. In this way, knowledge of dense matter physics supports the broader field of gravitational wave astronomy. Observations continue to reveal new behaviors. Some pulsars exhibit mode switching, where pulse shapes and timing properties change between distinct states. Others show intermittent emission turning on and off over weeks or months. These phenomena further complicate timing, but also provide more clues about magnetospheric and interior dynamics. The diversity of behaviors emphasizes that no two neutron stars are identical. Each is a laboratory with its own balance of forces, temperatures, and histories. The connection between microscopic physics and astronomical observation is especially clear in glitch studies. Quantum-scale pinning of vortices in nuclear matter leads to detectable changes in the arrival times of radio pulses traveling across thousands of light-years. Each pulse shift encodes information about forces acting deep inside a star. By gathering and analyzing these signals, astronomers indirectly explore matter at densities unreachable in terrestrial experiments. Future observatories will improve sensitivity to timing irregularities. Arrays of large radio telescopes, including the Square Kilometre Array, will detect many new pulsars and monitor known ones with higher precision. This will expand the sample of glitches and timing noise events, allowing statistical comparisons across populations. As the dataset grows, patterns will emerge, perhaps linking glitch behavior to age, magnetic field strength, or spin period more clearly. Each new measurement will refine the understanding of neutron star interiors and the dynamics of their superfluids and magnetospheres. In this way, the seemingly irregular ticks of pulsars serve as a continuous record of the physical processes at work inside neutron stars. Glitches, timing, noise, and related phenomena are not nuisances but essential clues. They reveal that these stars, though compact and dense, are active and evolving systems. Observers on Earth receive their signals as rhythmic pulses, but hidden within the rhythm are subtle deviations that tell the story of matter under extreme conditions. Among neutron stars, a special group stands out for the intensity of their magnetic fields. These are Magnetars objects with surface fields greater than 100 trillion Gauss. Their existence was inferred when astronomers observed bursts of soft gamma rays from apparently isolated sources. These bursts repeated irregularly, leading to the term soft gamma repeaters. Later, another class of objects called anomalous X-ray pulsars was found, radiating persistently in X-rays far more strongly than could be explained by rotation alone. Both groups are now understood as magnetars powered not by spin but by magnetic energy stored in their interiors and magnetospheres. The magnetic field of a magnetar exerts tremendous stress on the crust. Even though the crust is strong, capable of withstanding forces many times greater than any material on Earth, the field can twist and deform it. When the stress exceeds the breaking strain, the crust fractures. This sudden shift rearranges magnetic field lines in the magnetosphere, releasing energy as a burst of high-energy photons. The bursts last fractions of a second to a few seconds, yet they can outshine the rest of the galaxy in X-rays for that brief moment. Occasionally, magnetars unleash giant flares. These are much rarer events, recorded only a few times, but they demonstrate the extreme energy stored in magnetic fields. A giant flare begins with a spike of gamma rays lasting less than a second, followed by a pulsating tail that can continue for minutes. The tail reflects the trapped fireball of plasma confined by closed magnetic field lines, cooling and shrinking as it radiates. The energy released in the initial spike rivals the total output of the Sun over hundreds of thousands of years. Magnetars also emit persistent X-rays even when not bursting. This emission is thought to arise from heating of the crust and magnetosphere by magnetic stresses. The twisted field lines trap plasma which radiates steadily. Over time, as magnetic fields decay, the persistent emission weakens. This decay distinguishes magnetars from ordinary pulsars, which are powered by rotation rather than magnetic energy. The life of a magnetar is therefore governed by the evolution of its field, typically lasting only tens of thousands of years, before the field decays enough to quench activity. Observations of magnetars show spin periods in the range of 2 to 12 seconds, much slower than ordinary pulsars. Despite their slow rotation, their X-ray luminosities are high, confirming that rotation cannot power them. Their strong fields are inferred from the measured spin-down rates, which are consistent with torques exerted by fields exceeding 100 trillion Gauss. In some cases, spectral features provide direct confirmation of strong magnetic effects, such as the splitting of energy levels in atoms by the magnetic field called cyclotron resonance. The link between magnetars and other neutron stars remains an active area of study. Some ordinary pulsars may evolve into magnetars if their fields are amplified after birth, while others may be born with strong fields immediately. The process of dynamo action during the first seconds of a proto-neutron star's life is thought to generate magnetar-level fields if rotation is rapid enough. In this view, only a subset of neutron stars become magnetars depending on initial spin and convection properties. Magnetar activity can affect the surrounding interstellar medium. Bursts inject energy into the environment, heating and ionizing nearby gas. Giant flares can produce expanding radionebulae, as was observed after the 2004 flare from SGR 1806-20. These nebulae fade over months to years, tracing the release of energy into space. In this way, magnetars not only radiate directly, but also leave imprints on their surroundings that can be studied long after bursts subside. Some magnetar bursts show rapid oscillations in their tails, interpreted as seismic vibrations of the crust. These quasi-periodic oscillations provide a potential seismology of neutron stars. By measuring the frequencies, astronomers infer properties of the crust and magnetic field configuration. Though the signals are faint and challenging to analyze, they offer one of the few direct ways to probe the interior structure of a neutron star. Magnetars may also connect to other transient phenomena. A leading hypothesis for at least some fast radio bursts is that they originate from magnetars. In 2020, a fast radio burst was observed from a galactic magnetar, SGR 1935 Pulsars, of confirming that such stars can produce bright millisecond duration radio flashes. Whether all extragalactic fast radio bursts come from magnetars remains uncertain, but the link is now firmly established for at least some cases. This connection shows that magnetars, though rare, can produce signals visible across cosmological distances. The study of magnetars demonstrates the extremes of magnetic physics. Nowhere else are fields so strong or their effects so visible. They twist space around them, alter atomic structures, and dominate the energy budget of a star. Their activity reveals the close connection between magnetic stresses, crustal dynamics, and high-energy emission. By monitoring bursts, flares, and persistent emission, astronomers piece together the life cycle of these powerful objects. Magnetars eventually evolve into quieter neutron stars as their fields decay. Their bursts cease, and their emission fades. Yet during their active lifetimes, they provide unique insights into the behavior of matter under the influence of the strongest magnetic fields known in the universe. They remind us that even within the broader family of neutron stars, diversity is great, and each subclass highlights a different aspect of extreme physics. Magnetars, by their nature, display the dominance of magnetic fields, shaping not only the star itself, but also its environment and potentially signals observed far beyond our own galaxy. When a neutron star exists in a binary system, with another star, new physical processes come into play. If the companion evolves and fills its Roche lobe, matter can flow toward the neutron star. The intense gravity captures this material, which spirals inward. Instead of falling directly onto the surface, the gas forms an accretion disk. In this disk, friction and turbulence heat the gas to millions of degrees, causing it to radiate strongly in X-rays. Systems where this occurs are called X-ray binaries, and they are among the brightest X-ray sources in the sky. As matter from the disk approaches the neutron star, the magnetic field begins to dominate. For strong fields, the disk is truncated at the magnetospheric radius, where magnetic pressure balances the pressure of the inflowing gas. Inside this radius, plasma is forced to follow field lines channeling onto the magnetic poles. When it strikes the surface, it releases energy in concentrated hotspots, producing X-ray pulsations. These are observed as X-ray pulsars. The pulse profiles provide information about the field strength and geometry, as well as the accretion rate. In some binaries, the neutron star accretes directly from the stellar wind of a massive companion without forming a full disk. These wind-fed systems produce irregular X-ray emission reflecting the clumpy nature of stellar winds. Others exhibit stable accretion from a disk leading to more regular pulsations. The diversity of accretion behaviors arises from differences in companion mass orbital separation and magnetic field strength. Each system provides a different laboratory for studying accretion physics under extreme conditions. Accretion affects the neutron star itself. As gas flows onto the surface, it transfers angular momentum. Over long times, this can spin the star up to very high frequencies. This process explains the existence of millisecond pulsars. Observations of accreting systems confirm spin-up through detection of nearly coherent oscillations during thermonuclear bursts. When accretion ceases, the spun-up neutron star may shine as a stable millisecond radio pulsar, its magnetic field reduced compared to its youth. This recycling process demonstrates the close link between X-ray binaries and the population of old pulsars. Thermonuclear bursts provide another observable phenomenon. As accreted matter builds up on the surface, pressure and temperature rise until fusion ignites explosively. The result is a sudden flash of X-rays lasting seconds to minutes called a type I X-ray burst. These bursts repeat as the surface reaccumulates fuel. Their light curves and spectra provide information about the surface composition, nuclear reactions, and even the neutron star's radius. In rare cases, superbursts occur powered by carbon fusion deep in the crust lasting hours and releasing immense energy. Accretion also changes the magnetic field. Continuous inflow of plasma can bury field lines beneath the surface, reducing the observable dipole strength. This explains why many millisecond pulsars appear to have weaker fields. Over time, the buried fields may diffuse outward again, but the process is slow. Thus, the history of accretion leaves a long-term imprint on the magnetic properties of the star. In close binaries, accretion can proceed at very high rates, leading to luminous X-ray emission near the Eddington limit where radiation pressure balances gravity. In some systems, matter is funneled into collimated jets launched perpendicular to the disk. These jets emit in radio and sometimes in X-rays, indicating that neutron stars like black holes can drive relativistic outflows. Observations of such jets provide insight into how compact objects convert accretion energy into directed flows, a process still not fully understood. Not all interactions involve steady accretion. Some binaries are transient, alternating between bright outbursts and long quiescent phases. During outbursts, enhanced mass transfer lights the system in X-rays. During quiescence, emission drops, allowing astronomers to study the cooling of the neutron star's crust heated during accretion. Monitoring this cooling reveals thermal conductivity and heat capacity of dense matter. In this way, transients provide alternating windows into both accretion dynamics and crustal physics. The orbital dynamics of binaries also play a role. In some systems, neutron stars orbit massive companions with eccentric orbits, leading to periodic episodes of enhanced accretion near periastron. In others, close circular orbits produce continuous accretion. Measuring orbital periods and mass functions allows determination of neutron star masses essential for constraining the equation of state. Some of the most massive known neutron stars, close to 2 solar masses, were measured in binary systems through such methods. Accretion episodes may trigger additional phenomena. When gas builds up unevenly, instabilities in the disk can lead to quasi-periodic oscillations in X-ray brightness. These oscillations trace orbital motion of matter near the neutron star and probe strong gravity regimes. High-frequency oscillations correspond to orbital periods of milliseconds, placing constraints on the size and mass of the star. Thus, variability in X-ray binaries encodes information about spacetime near neutron stars. The study of accreting neutron stars is therefore multidimensional. Observations reveal disk structure, magnetic channeling, surface explosions, spin evolution, and jet launching. Each process links small-scale nuclear and plasma physics with large-scale astrophysical behavior. Long-term monitoring has shown how neutron stars evolve from accreting systems into recycled millisecond pulsars. In turn, these pulsars serve as tools for fundamental physics. The cycle demonstrates the interconnectedness of neutron star phenomena across different stages of life. From the perspective of observers, X-ray binaries are laboratories for extremes. They display some of the brightest bursts, fastest spins, and strongest gravitational effects accessible to telescopes. Each accreting system provides a slightly different arrangement of mass field and orbit, offering a wide survey of physical conditions. Through them, scientists probe accretion under relativistic gravity-plasma interactions with intense magnetic fields and the equation of state of dense matter. These systems reveal that neutron stars are not passive remnants, but active participants in binary evolution continually reshaped by the flow of matter from their companions. When two neutron stars orbit each other in a binary system, their fate is governed by the emission of gravitational waves. General relativity predicts that accelerating masses radiate energy in the form of ripples in spacetime. For a binary, this energy loss causes the orbit to shrink slowly. As the stars spiral closer, the orbital period decreases and the frequency of emitted waves rises. Over millions or billions of years, the orbit decays until the stars finally merge. The inspiral phase is long and gradual, but the last minutes accelerate dramatically, culminating in a collision of extraordinary violence. During the early stages of inspiral, the gravitational waves are faint, detectable only with very sensitive instruments. The amplitude grows as the stars approach. The waveform encodes information about the masses, spins, and tidal deformabilities of the stars. By analyzing the detailed shape of the signal, astronomers infer properties of dense matter that cannot be studied otherwise. The first detection of such an event occurred in 2017 when LIGO and Virgo recorded a binary neutron star merger. The event lasted over a minute in the detectors, with frequency sweeping from tens to hundreds of hertz as the stars spiraled together. Tidal effects become important in the late inspiral. Each star raises tides on the other, deforming its shape. The degree of deformation depends on the equation of state, since stiffer matter resists stretching more strongly. These deformations accelerate orbital decay slightly, leaving an imprint on the waveform. Careful modelling of this signature provides direct constraints on neutron star radii and internal stiffness. Thus, mergers serve as cosmic experiments, probing how matter behaves at densities several times nuclear saturation. As the stars reach contact, the dynamics become highly nonlinear. Numerical simulations using supercomputers are required to follow the final milliseconds. The outcome depends on the total mass and the equation of state. In some cases, the merger forms a hypermassive neutron star temporarily supported by rotation and thermal pressure. This remnant may survive for milliseconds to seconds before collapsing into a black hole. In other cases, collapse occurs almost immediately. The distinction leaves different observational signatures, especially in the electromagnetic emission that follows. The collision expels material at high velocities. Some of this ejecta is thrown out tidally in spiral arms composed of neutron-rich matter. Other material is driven out by shocks and winds from the remnant. The amount and composition of this ejector determine the brightness and color of the kilonova that follows. The merger also creates conditions for the synthesis of heavy elements through rapid neutron capture. Gold, platinum, and other R-process elements are thought to be produced mainly in such mergers. In this way, neutron-star collisions contribute directly to the chemical enrichment of galaxies. Short gamma-ray bursts are another product of mergers. If a black hole forms surrounded by a dense accretion disk, conditions are favorable for launching a relativistic jet. When this jet points toward Earth, it produces a burst of gamma rays lasting less than 2 seconds. Afterglows follow in X-ray, optical and radio bands as the jet interacts with interstellar gas. The 2017 event confirmed this connection, as a short gamma-ray burst was observed within seconds of the gravitational wave detection, though seen slightly off-axis. This multi-messenger observation firmly established the link between neutron-star mergers and short gamma-ray bursts. Gravitational wave data combined with electromagnetic observations yield a comprehensive picture. The gravitational waves reveal the inspiral and merger dynamics. The gamma-ray burst and afterglows reveal jet formation. The kilonova reveals the ejector and nucleosynthesis. Together they provide an unprecedented view of physics under extreme conditions. The 2017 event marked the beginning of multi-messenger astronomy. With neutron-star mergers and future detections will expand this field. Inspirals also serve as precise tests of general relativity. The waveform matches theoretical predictions with high accuracy, confirming the theory in the strong field regime. Deviations could reveal new physics, but so far no significant anomalies have been seen. The ability to measure the speed of gravitational waves directly by comparing their arrival with light from the same event confirmed that they travel at essentially the speed of light. This placed strong constraints on alternative theories of gravity. The population of binary neutron stars is growing in observational records. Many are found as double pulsars, where both stars are detectable as radio pulsars. These systems allow precise measurement of orbital decay due to gravitational wave emission matching predictions over decades. They serve as laboratories in advance of mergers, showing the gradual inspiral at earlier stages. Eventually some of these systems will merge, though most will do so long after current observational timescales. The astrophysical importance of mergers extends beyond fundamental physics. They may play a role in galaxy evolution by distributing heavy elements. They may also influence rates of star formation by injecting energy into the interstellar medium. The frequency of such mergers in the universe remains a subject of active measurement. Each gravitational wave detection helps refine the rate, which in turn constrains models of binary stellar evolution. From beginning to end, the story of a binary neutron-star merger is one of gradual energy loss, followed by sudden transformation. For billions of years, the stars orbit quietly, emitting faint gravitational waves. In the last minutes, the inspiral accelerates, the waves grow louder, and the stars collide. The aftermath shines across the spectrum and forges elements essential to planets and life. Observers on Earth with detectors tuned to gravitational and electromagnetic signals can watch these cosmic laboratories in action, drawing lessons about matter gravity and the origins of elements. When two neutron stars collide, the consequences extend beyond the gravitational waves that announce the merger. The collision often produces a jet of material moving at nearly the speed of light. These relativistic jets are thought to power short gamma-ray bursts, flashes of high-energy photons lasting less than 2 seconds. The mechanism involves a compact remnant, usually a black hole surrounded by a dense accretion disk. Magnetic fields and rapid rotation launch a narrow outflow along the rotation axis. If this jet points toward Earth, observers detect an intense but brief gamma-ray signal. If it is misaligned, only weaker afterglows may be seen, yet these still carry information about the event. The 2017 merger designated G-287 demonstrated this process clearly. Just over a second after the gravitational wave signal ended space, telescopes detected a short gamma-ray burst. The burst was weaker than typical because the jet was not directed precisely toward Earth. Still, the afterglow in X-ray optical and radio bands traced the expanding jet as it interacted with surrounding interstellar gas. Over weeks and months the afterglow brightened, peaked, and then faded, matching predictions of an off-axis jet gradually spreading sideways. This observation confirmed long-standing theories that short gamma-ray bursts originate from neutron star mergers. The structure of jets remains a subject of study. Some models propose a narrow uniform core surrounded by slower-moving material. Others suggest a continuous angular structure, with velocity and energy declining smoothly away from the axis. Observations of afterglows support structured jets rather than simple uniform beams. The details matter because they influence how many bursts are visible from Earth and how their energies are distributed. Structured jets also explain why many mergers may produce gamma-ray bursts, but only a fraction are seen directly due to orientation. Jets are powered by immense amounts of energy. Accretion onto the central remnant releases gravitational energy that can drive outflows. Magnetic fields anchored in the disk and remnant channel this energy into narrow beams. The composition of the jets is still debated. They may contain mainly leptons and magnetic fields, or they may carry significant baryonic matter. Their composition influences how efficiently they radiate and how they interact with surrounding material. Simulations attempt to model these processes, but uncertainties remain, especially in how jets break through the dense ejector launched during the merger. The interaction between jets and ejector produces additional observable effects. As the jet pushes through, it shocks the material, creating a cocoon of hot plasma. If the jet fails to break out, the cocoon itself may produce observable emission. Such choked jets could explain some faint transients seen in gamma rays and X-rays. Thus, even when no bright burst occurs, mergers may still produce signatures through jet-ejector interactions. Multi-wavelength observations are essential for understanding jets. Gamma-ray satellites detect the initial burst. X-ray and radio telescopes follow the afterglow as the jet decelerates. Optical observations monitor the kilonova, which overlaps in time but arises from different material. Together, these data provide a comprehensive view of the merger and its aftermath. The timing and brightness of each component reveal the geometry, energy, and composition of the outflows. The association between neutron star mergers and short gamma-ray bursts also explains the distribution of bursts across the sky. Unlike long gamma-ray bursts, which are linked to massive star deaths and trace star-forming galaxies, short bursts occur in both star-forming and older galaxies. This matches expectations since neutron star binaries can take billions of years to merge after their formation. Some are observed far from their host galaxies, consistent with kicks imparted at birth that sent them drifting into intergalactic space before merging. The energetics of short bursts are immense. Though brief, they release as much energy in gamma rays as the Sun radiates in its entire lifetime. This underscores the efficiency of compact object mergers in converting gravitational energy into radiation. After the burst, the jets continue to radiate as afterglows for months or years, allowing long-term study of their physics. Each detection adds to the catalogue, improving statistics on their rates, energies, and environments. Short gamma-ray bursts are also valuable for cosmology. By comparing gravitational wave distances with redshift measurements of host galaxies, astronomers can derive independent estimates of the Hubble constant, the current expansion rate of the universe. This method, called a standard siren, does not rely on traditional distance ladders. The 2017 event provided the first such measurement, though, with significant uncertainty. Future events will refine the value, potentially resolving the current tension between different methods. The role of jets extends beyond observable bursts. They also affect the dispersal of heavy elements created in the merger. By ploughing through ejector jets, redistribute material and mix it into the surrounding medium. This mixing may influence the morphology of kilonovae and the eventual distribution of R-process elements in galaxies. Thus, jets contribute not only to transient signals, but also to long-term chemical enrichment. While much progress has been made, key questions remain. How exactly are jets launched from compact remnants? What sets their structure and composition? How common are choked jets compared to successful ones? Upcoming observatories will help answer these questions. The next generation of gravitational wave detectors will localize mergers more precisely, while sensitive X-ray and radio facilities will track afterglows in detail. Coordinated observations across the spectrum will build a larger sample of events, revealing patterns that individual detections cannot. In studying relativistic jets from neutron star mergers, astronomers probe some of the fastest and most energetic flows in the universe. These jets convert gravitational collapse into beams of radiation visible across billions of light-years. They link compact object physics with high-energy astrophysics and cosmology. Each burst, though fleeting, carries information about the dense matter at the heart of the merger and the dynamics of energy release under extreme conditions. One of the most profound consequences of neutron-star collisions is the creation of heavy elements. When two stars merge, large amounts of neutron-rich matter are ejected at high speeds. In this, material conditions favour what is known as the rapid neutron capture process, or R process. In the R process, atomic nuclei capture neutrons much faster than they can decay. This allows the build-up of extremely heavy nuclei, some of which then decay into stable elements such as gold, platinum, and uranium. The R process had long been proposed as the origin of these elements, but the direct confirmation came only after the first observed neutron-star merger in 2017, when the accompanying kilonova displayed light curves and spectra consistent with freshly synthesized heavy nuclei. The physics of R-process nucleosynthesis depends on both the amount of ejecta and its composition. Material ejected dynamically during the merger is extremely neutron-rich. As neutrons flood nuclei, the R-process path moves far from stability. When the supply of neutrons ends, the unstable nuclei decay back towards stability, emitting beta particles and gamma rays. This radioactive decay releases heat that powers the kilonova emission. The opacity of the ejector, controlled by the abundance of lanthanides and actinides, determines the color and timescale of the kilonova light. If the ejecta are rich in lanthanides, the opacity is high, producing a redder and longer-lasting signal. If fewer lanthanides are present, the emission peaks earlier and appears bluer. Observations of the 2017 kilonova revealed both components. An early blue emission peaked within a day, indicating a portion of ejecta with moderate neutron richness. Later, a redder component dominated, lasting for weeks, pointing to lanthanide-rich material. Together, these signals confirm that neutron-star mergers produce both light and heavy R-process elements. The total mass of synthesized material was estimated to be several hundredths of a solar mass, enough to explain a significant fraction of the universe's supply of gold and platinum if such events occur frequently enough across cosmic history. the importance of mergers in galactic chemical evolution lies in their contribution relative to other possible sources. For decades, core collapse supernovae were considered as potential R-process sites. While some supernova models still allow for limited R-process production, the conditions appear less favorable than in mergers. The extreme neutron richness and relatively large ejector masses in mergers provide a more robust explanation. Models of chemical evolution in galaxies now include neutron star mergers as major contributors to heavy element enrichment. Their predicted rates and yields match observed abundances in stars, though debates continue over the exact balance with other sources. Detailed nucleosynthesis calculations require knowledge of nuclear properties far from stability. Many of the isotopes involved in the R process have never been produced in laboratories. Their decay rates, neutron capture cross-sections, and fission probabilities must be estimated from theory. These uncertainties affect predictions of final element abundances. Experiments at new rare isotope facilities are gradually providing data to improve these models. By combining nuclear physics measurements with astrophysical observations of kilonovae, scientists refine the picture of how heavy elements form. The radioactive decay of R-process nuclei not only powers kilonovae, but also leaves longer-term signatures. For example, isotopes with half-lives of millions of years contribute to the heating of planetary interiors. On Earth, uranium and thorium decay still supply heat that drives plate tectonics. The origin of these elements in neutron star mergers means that the geological activity of planets is indirectly connected to stellar collisions in the distant past. The link between cosmic events and planetary habitability highlights the far-reaching consequences of R-process nucleosynthesis. Spectroscopy of kilonovae provides direct observational tests. The spectra contain broad absorption features caused by complex atoms with many electron transitions, especially lanthanides. Although modeling these spectra is challenging due to incomplete atomic data comparisons, confirm the presence of heavy elements. Future kilonova detections with more sensitive instruments will allow identification of specific elements, providing even stronger evidence. Observations across ultraviolet, optical, and infrared wavelengths are crucial, since different elements dominate different bands. The variety of ejector channels in mergers further complicates the picture. Dynamical ejecta launched during the collision are extremely neutron-rich. Winds driven from the remnant disk or neutron star are less neutron-rich, producing lighter R-process elements. Neutrino irradiation from the remnant can alter the composition, changing the balance between light and heavy elements. The interplay of these processes explains the diversity of kilonova signatures observed or predicted. Some events may produce mainly lighter R-process elements, while others yield the full range up to uranium. The observed diversity in stellar abundances across the Milky Way may reflect this variation in merger conditions. The timescales of chemical enrichment also matter. Neutron star mergers occur after the lifetimes of massive stars, since binaries must survive supernova explosions and spiral together over millions to billions of years. Early galaxies show R-process elements in old stars, suggesting that either some mergers occur very quickly, or additional R-process sources contribute. This remains an active research area, with some models proposing that certain types of supernovae also produce R-process nuclei complementing the merger contribution. The relative roles of these sources continue to be debated, but mergers are now firmly established as at least one major source. From an observational perspective, the combination of gravitational wave detection and kilonova light provides a direct probe of nucleosynthesis. The gravitational waves reveal the total mass and dynamics of the merger, while the kilonova emission shows how much mass was ejected and how it decayed. By comparing events with different properties, astronomers will learn how variations in mass ratio spin and equation of state influence our process yields. Each new detection adds another data point in building a comprehensive picture of heavy element production in the universe. The study of our process nucleosynthesis in neutron star mergers unites nuclear physics, astrophysics, geology, and cosmology. It links the fundamental forces that bind nuclei to the cosmic events that forge elements, and finally to the composition of planets and life. Gold in jewelry, iodine in biology, uranium in the Earth's core, all may trace their origins to the collision of neutron stars in ancient galaxies. Observations of kilonovae make this connection tangible, showing the universe creating heavy matter before our eyes. Gravitational waves provide one of the most direct ways to probe neutron star interiors. When two neutron stars spiral together, the emitted waves carry a precise record of their orbital evolution. The waveform depends on the masses and spins of the stars, but also on how easily each star deforms under tidal forces. This deformability is set by the equation of state, the relation between pressure and density at extreme conditions. By measuring tidal effects in the waveform, astronomers can constrain the stiffness of matter inside neutron stars. This approach complements observations of mass and radius from electromagnetic signals, creating a multi-messenger framework for understanding dense matter. The first detection of gravitational waves from a neutron star merger, GW1 Centaurus 817, demonstrated this potential. Analysis of the signal showed that neutron stars cannot be extremely soft, otherwise the tidal effects would have been much stronger, nor can they be extremely stiff, which would have produced weaker signals. Instead, the data pointed to an intermediate stiffness consistent with radii between about 11 and 13 kilometers for stars of average mass. These constraints excluded many theoretical models that had predicted either very small or very large radii. As detectors improve, future events will refine these measurements. Third-generation instruments such as the Einstein Telescope and Cosmic Explorer will detect mergers with far greater sensitivity. They will observe many more cycles of inspiral, providing sharper measurements of tidal deformability. With hundreds of detections, the allowed range of equations of state will narrow significantly, potentially distinguishing between nucleonic matter and exotic states such as quark matter. In this way, gravitational waves will gradually solve the long-standing question of what lies inside neutron stars. Gravitational wave signals also test general relativity and the strong field regime. The precise phasing of the waveform matches the predictions of Einstein's theory across thousands of cycles. Any deviations would indicate new physics such as modifications to gravity at high curvature. So far, no significant deviations have been found, reinforcing the accuracy of general relativity. The speed of gravitational waves was measured directly by comparing their arrival with light from the same event. They were found to travel at essentially the same speed as light within tiny margins, placing tight limits on alternative theories. Electromagnetic observations provide independent constraints. X-ray telescopes such as NICER measure pulse profiles from hotspots on rotating neutron stars. The way gravity bends light depends on mass and radius, so careful modeling yields constraints on both. Recent results suggest radii around 12 kilometers for stars of about 2 solar masses consistent with gravitational wave measurements. By combining both approaches, uncertainties shrink further. This synergy between electromagnetic and gravitational data exemplifies the power of multi-messenger astronomy. Cooling observations add another dimension. As neutron stars lose heat through neutrino emission, The rate depends on whether fast processes such as direct Earker are allowed. If protons are too scarce, only slower modified Earker processes occur, leading to gradual cooling. If the proton fraction exceeds a threshold, direct Earker accelerates cooling. Observations of young neutron stars like the one in Cassiopeia show cooling rates consistent with the onset of neutron superfluidity and proton superconductivity. These findings link astrophysical data with microscopic pairing interactions in nuclear matter. Glitch behavior discussed earlier provides yet another probe. The sudden transfer of angular momentum from the superfluid interior to the crust shows that vortices are pinned and unpinned in large numbers. The statistics of glitches reveal how strongly the crust and core couple. This information constrains the fraction of the star's moment of inertia contained in the crust, which depends on the equation of state. Thus, even timing irregularities contribute to the effort of pinning down dense matter properties. The importance of combining all these signals cannot be overstated. No single observation is sufficient to determine the equation of state. Mass measurements set lower bounds. Radii from X-rays set size constraints. Gravitational waves measure tidal deformability. Cooling tracks test neutrino processes. Glitches reveal superfluid properties. Together they form a consistent picture that gradually excludes unrealistic models. The result is a narrowing corridor of possibilities that guides theorists toward a true description of matter at the highest densities. Uncertainty still surrounds the possible presence of exotic particles or phases. Hyperons containing strange quarks may appear at several times nuclear density. Their presence would soften the equation of state, reducing the maximum mass. Yet the existence of neutron stars with nearly 2 solar masses challenges this idea unless repulsive interactions counterbalance the softening. Deconfined quark matter is another possibility. If it appears gradually, the effect on observable properties may be subtle. If it appears suddenly, stars above a certain mass may collapse more readily or display distinct structural changes. Gravitational waves from mergers could reveal such transitions through unexpected features in the waveform. The detection of post-merger signals is especially promising. After the stars collide, the remnant oscillates violently, emitting gravitational waves at kilohertz frequencies. These signals are currently beyond the sensitivity of existing detectors, but future instruments may capture them. The frequencies and damping times of these oscillations depend directly on the equation of state. Observing them would provide a decisive measurement of dense matter properties. In addition to gravitational and electromagnetic observations, neutrinos may one day provide direct probes. A nearby supernova that leaves a neutron star remnant would release a burst of neutrinos carrying information about the proto-neutron star's interior. Although such an event is rare, future neutrino detectors are prepared to capture it when it occurs. Together, the gravitational waves and light neutrinos would complete the triad of messengers, probing dense matter from multiple angles. Multi-messenger observations also offer cosmological applications. Gravitational waves provide an absolute measure of distance independent of the cosmic distance ladder. When combined with redshift from host galaxies, they yield values of the Hubble constant. This standard siren method provides an independent check on cosmic expansion. With enough events, the tension between different measurements of the Hubble constant may be resolved. Thus, the study of neutron star mergers extends beyond astrophysics into cosmology. In summary of this explanatory thread, gravitational waves, X-rays, cooling curves, glitches, and future neutrino detections all contribute to constraining the equation of state. Each observation narrows the possibilities for how matter behaves under the most extreme pressures. Neutron stars therefore serve as cosmic laboratories, their signals carrying information from conditions unreachable on Earth. As detectors grow more sensitive and observations accumulate, the mysteries of dense matter will continue to give way to precise knowledge step by step. Neutron stars do not exist in isolation from their environments. As they move through the galaxy, they interact with the interstellar medium, leaving visible traces. One form of interaction is the creation of a pulsar wind nebula. The rotation and magnetic field of the star drive a continuous outflow of relativistic particles called a pulsar wind. When this wind collides with surrounding gas, it forms a shock that accelerates particles and produces bright emission. The Crab Nebula is the best known example, powered by the central pulsar. It glows across the spectrum from radio to gamma rays with fine structures such as wisps and jets, shaped by the pulsar's magnetic field. These features evolve over months, showing that pulsar winds are dynamic and highly energetic. Not all pulsars produce large nebulae. The outcome depends on the age, spin-down power, and surrounding density. Young pulsars with strong winds inflate large nebulae, while older pulsars with weaker winds produce smaller structures or none at all. Still, even modest pulsar wind nebulae provide information about the energy output and magnetic geometry of their central stars. The shape of the nebula reflects how the wind interacts with its environment, revealing anisotropies in the outflow. By studying these nebulae, astronomers gain indirect views of the magnetosphere and particle acceleration processes near the star. Another form of interaction occurs when a pulsar moves rapidly through the interstellar medium. Many neutron stars receive kicks at birth, propelling them at hundreds of kilometers per second. As they plow through gas, their winds create bow shocks, much like the bow wave of a ship. These bow shocks can be observed in H-alpha emission X-rays or radio, depending on the properties of the gas. The resulting structures trace the pulsar's path and velocity. Some bow shocks extend for light years, marking trails of neutron stars across space. The direction and shape provide clues about the local density of interstellar matter and the speed of the star. Supernova remnants are also linked to neutron stars. When the progenitor star explodes, it leaves behind an expanding shell of gas. If a neutron star remains at the center, its wind can energize the remnant-producing composite structures with both shell and nebular emission. Over thousands of years, the remnant expands and fades, but the neutron star continues to inject energy. Studying these systems connects the birth of neutron stars to their later evolution, showing how supernovae seed the interstellar medium with heavy elements and energetic particles. The interaction between pulsars and the interstellar medium also affects observations. As radio pulses travel through ionized gas, they are dispersed with lower frequencies, delayed more than higher ones. Measuring this dispersion allows astronomers to calculate the column density of electrons along the line of sight. In this way, pulsars serve as probes of the interstellar medium, mapping its structure across the galaxy. Scattering by irregularities in the plasma further broadens the pulses, revealing turbulence in interstellar gas. These propagation effects are not nuisances but valuable diagnostic tools. Some pulsars emit giant pulses, sporadic bursts of radio emission, far brighter than their normal pulses. The Crab pulsar is a classic example. These giant pulses, when observed through interstellar scattering, provide especially sensitive probes of plasma turbulence. By combining pulsar timing with propagation studies, astronomers build a detailed picture of both the stars themselves and the medium they traverse. This dual role makes pulsars unique as both objects of study and tools for studying the galaxy. Interactions also occur in binary systems where neutron stars accrete from companions. Outflows from these systems can influence surrounding gas, sometimes creating jets or bubbles. In globular clusters, dense environments lead to many recycled millisecond pulsars whose winds and radiation affect nearby stars. These collective effects shape the dynamics and chemistry of their environments on cluster scales. Thus, neutron stars contribute not only locally, but also on larger astrophysical scales. High-energy emission from pulsar wind nebulae and bow shocks connects neutron stars to cosmic rays. Some fraction of the cosmic rays reaching Earth may originate from pulsar-driven acceleration. Electrons and positrons accelerated in shocks contribute to the high-energy lepton population in the galaxy. Observations of nearby pulsars and their nebulae provide constraints on this contribution. In this way, neutron stars may play a role in one of the longest-standing questions in astrophysics, the origin of cosmic rays. Over long timescales, neutron stars cool and spin down their emissions, weakening. Yet even as isolated remnants, they continue to interact with their surroundings through motion and magnetism. Some become dim thermal X-ray sources detectable only as faint glows. Others remain visible as pulsars for millions of years. Eventually, most fade below detection thresholds, joining the unseen population of dead neutron stars in the galaxy. Estimates suggest that hundreds of millions of such objects exist, though only a fraction have been discovered. The study of neutron stars is therefore never confined to the stars themselves. Their winds shape nebulae. Their motions carve bow shocks, their pulses probe interstellar plasma, and their remnants enrich galaxies. From their violent births in supernovae to their quiet passages through interstellar space, neutron stars remain active participants in the life of the cosmos. Each interaction reveals a new facet of their nature, linking microscopic physics of dense matter to macroscopic structures spanning light years. By observing these interactions, astronomers connect the internal processes of neutron stars with the broader galactic environment. The Crab Nebula shows the ongoing energy release of a young pulsar. Bow shocks trace the high velocities imparted at birth. Kilonovae mark the dispersal of heavy elements forged in collisions. Each phenomenon is a piece of the larger puzzle, illustrating how neutron stars, though tiny in size, exert vast influence across space and time.